Good evening. We have some people still coming in. There's a lot of open seats in the middle. Please make yourself comfortable. I'm Richard Meserve. I'm the president of the Carnegie Institution, and I'm very pleased to welcome you all to a Capital Science lecture. This evening's lecture is co-hosted by Carnegie along with the embassies of Switzerland and Italy. And we have this connection because we have the good fortune this evening to be hearing a lecture from a winner of one of the Balzan Prizes. Balzan is a foundation, is one that exists in both Italy and Switzerland for some complicated reasons that I'll let someone else explain. But in any event, it's a very prestigious award. It's one that has some resonance with Carnegie, in that we were established by Andrew Carnegie to find the means to support exceptional people in the conduct of science. And that aligns completely with the objectives, at least in part, of the Balzan Foundation, which seeks to give awards to individuals who have achieved great excellence in their scientific work. I'm very pleased that 3 Carnegie scientists, including one who's here this evening, Russ Hemley, were previous recipients of the Balzan Prize, so we have a special affection for the Balzan Foundation. But in any event, I wanted to welcome you all this evening and also to introduce His Excellency Ambassador Manuel Seger, who is the ambassador from Switzerland.
Dear Dr. Meserve, thank you very much for your kind introduction. Distinguished guests, good evening. It's a great pleasure to be here at this beautiful venue for the 2010 Balzan lecture, which this year will be given by Professor Grätzel. As many of you know, the Balzan lecture here in Washington is both a Swiss-Italian tradition, as Dr. Meserve already pointed out. It's a Swiss-Italian tradition, but at the same time, it's also a part of the Carnegie's own Capital Science evening lectures. We're here, as I said, to listen to Professor Grätzel this evening. He was born in Germany. He's a Swiss citizen now. We do that sometimes in Switzerland. We let people be born somewhere else, and then we, once they're famous, we nationalize them and claim them as one of our own. He's a professor. Professor Grätzel is a professor at the École Polytechnique Fédérale at Lausanne in Switzerland, and he was awarded the Balzan Prize for, and I quote, his many contributions to the science of new materials, and in particular for his invention and development of a new type of photovoltaic solar cell, the dye-sensitized cell, commonly known as the Grätzel cell. It just goes to show that size doesn't matter when it comes to having things named after you. What is the connection to the Balzan Foundation to Switzerland? It's actually Mr. Balzan, Eugenio Balzan, in 1933, in opposition to fascism in his native Italy. He moved to Switzerland, where he lived in Zurich and Lugano, and for 20 years, and also died there. In honor and in memory of her father, Angela Lina Balzan set up this foundation, this Eugenio Balzan International Foundation, to encourage humanitarian, social, scientific, and artistic endeavors. Since 1961, over 100 laureates have received this prestigious award, which is in fact one of the prestigious awards, one of the most prestigious awards in the sciences and humanities. The annual award-giving ceremony is alternatingly held in Switzerland and in Italy, in Zurich and Milan, to be specific, and it's always attended by the respective heads of state. The foundation has two offices, one in Milan and one in Zurich, the Prize Foundation, which is headquartered in Milan, and the Fund Foundation, which is headquartered in Zurich. Incidentally, the distance between the two cities has just gotten smaller a few weeks ago with the world's longest train tunnel, about, if I'm not mistaken, 36 miles. That has been now established as the longest tunnel, and it cuts the train time by 1 hour between the two cities, which in itself is a scientific and technological achievement. I would like to congratulate you, Professor Grätzel, on winning this prestigious Balzan Award, and I would like to thank you for being our lecturer this evening. Professor Grätzel received, as I mentioned, received the award for his invention of the solar cell, named after him, and the prize was awarded in recognition of your contribution to a global challenge, which is the sustainable production of energy. This evening's event is in itself a reflection of the global dimension of your achievement, Professor Grätzel, a German-born Swiss, working, lecturing in the French part of Switzerland, giving a lecture here in the United States, co-sponsored with the Italian embassy. That in itself is a sign, as I said, of the global dimension of your work and of your achievement. And I wish all of us an inspiring and interesting evening with your lecture. Thank you very much for your attention.
Good evening. My name is Alberto Devoto. I'm scientific attaché at the Embassy of Italy. Unfortunately, the ambassador Giulio Terzi could not come because of previous commitments, but he told me please to say hello and to congratulate for this wonderful event that we're going to have here this evening. I'm here because I would like to introduce a little bit the argument of the topic of today's presentation. And they gave me some notes, or I prepared some notes for this event, and then I decided maybe I should not read them because I don't read very well without my glasses, and I forgot my glasses, and that is one problem. But this is not the entire story. The reason is that the ambassador from Switzerland mentioned something that I really feel very strongly about. He mentioned about the scientific, the international side of science. And today we're going to have a marvelous presentation that has to do with something that all of us share, the sun. The sun is international. It does not belong to anyone. It's of all of us. All of us can benefit from it. And Dr. Grätzel, with his discovery, with his work, is making for all of us easier to use the sun. This is really something that always I'm amazed. I mean, really, everybody now complains that there is not enough funds for research. Research is becoming more expensive, or maybe scientists become more demanding. I don't know what is the truth. But I think that if science becomes international, the load for everybody becomes lighter. And that is what I think this should be the message of today. The discovery of a great scientist makes, in a sense, life better for everybody because all of us can use better an international good, which is the sun that shines for all of us. Now, there is another thing that I would like to mention, and the essence of, or the starting point for the discovery of Dr. Grätzel is the photovoltaic effect. And this is, again, I noted that there are many students here from a school in Virginia, not West Virginia, in Virginia. And for me, it's a pleasure when I can talk with young students, because here I can tell you another story. Dr. Grätzel teaches in a French, in the French part of Switzerland, in Lausanne, and this discovery that is linked to photovoltaic effect is due to a French scientist. But what is marvelous about it is that it was a family of scientists, 4 generations of great scientists. The first one, I'd always remember the name of the first one. I don't know why. I always know the one that was responsible for radioactivity, and it's called Becquerel, who got the Nobel Prize for that. But there are also the other ones, and these I have to read. First of all, there is the father of all of them, which is Antoine César Becquerel, who was actually involved in the discovery of, I don't know if my pronunciation is correct me if I'm wrong, piezoelectricity. That is the electricity you produce in a certain way, and I think you should read about it. I mean, I think it's much better, instead of listening from me my broken English, you can read it in a book much better, and you find. But then there is the son of Antoine, whose name was Alexandre Edmond, and he is really the father of photovoltaic effect, and also the father of Henri Becquerel, who was really one of the persons responsible for some studies in radioactivity, which is also another source of energy, maybe not as clean as solar energy, but also another important source of energy, and also very important and useful tool in many things. And finally, there was the son of Henri Jean, who was also a scientist. So there is 4 generations of great scientists. But before I quit, I would like to tell you a few things of the good. The work of Dr. Grätzel is going to be presented by him. He's going to tell you what he does. But I would like to tell you a little bit more about his accomplishments, which have been recognized by many important universities that have given him, in Italy it's called laurea honoris causa, which is honorary degrees, but it sounds better if I say it in Latin, laurea honoris causa, which is, it sounds more impressive. I don't know if it is better, but I mean, it looks better impressive. And he received many important prizes, among them the Harvey Prize. He got a prize from Città di Firenze, which I think is also an Italian prize, but he got many more. And his biography is really very impressive. So I don't want to take too much of your time, and let me introduce Dr. Grätzel, and he's going to talk about light and energy mimicking natural photosynthesis. Give a welcome to Dr. Grätzel.
Thank you, Alberto. This very flattering remarks. I feel humbled. And, Your Honor, Mr. President, distinguished guests, ladies and gentlemen, and dear students, it's a pleasure to be here tonight and talk to you about our research. And it's an honor to present the Balzan lecture. It's a named lecture, and I was very fortunate to be given the Balzan Award last year, and we had also the symposium, the Balzan Forum, and I was so delighted to see Ruud Dreyfus, our former president and federal councillor, being in that lecture and congratulating me. And so it's been and I received the award actually from Doris Leuthard, who is now this year our current president. It is true that I'm of German origin, and I'm a Swiss citizen, and I teach in French. And I have an American wife, a Texan wife. So I'm married to America in a way. And so it's a global, very global picture. The ambassador has pointed very correctly. So the Balzan Award is a very prestigious award that has a considerable amount of funding along. And I should mention to young people that the Balzan Foundation decided to split it. So only half to the laureate, the other half is used to fund young scientists. And so it's been for me a tremendous help to have this award to help engage a young, brilliant student from Ashwini from India. She was extremely grateful and to have this opportunity to come to Switzerland. And she has been doing a marvelous job. So again, I'd like to express my gratitude again to the Balzan Foundation and the prize committee for having bestowed that honor on me. So tonight we will be talking about the conversion of light into electrical energy. So it's a photovoltaic effect. But Volta was Italian, so the name photovoltaic comes from Volta, and so electricity was really discovered by Galvani and Volta. So a long tradition. We have been working on this scientific question for a long time. It was first a curiosity-driven research, but also mission-oriented. We had in mind to, first of all, to understand better what the plant was doing. And 30 years ago, the knowledge in this field was not so far advanced like today. And so I participated in this revolution. More and more people learning about what the intricacies are of natural photosynthesis. Some of you might know that in natural photosynthesis, you have the green dye is called chlorophyll, and that's what makes the leaf look green. And so what is the role of chlorophyll? Well, it captures sunlight and produces electric charges. Now, you don't see electric current coming out of the green leaf, and that's because the plant uses these electric charges immediately to convert them in chemical reaction to the carbohydrates. The carbon dioxide produces the carbohydrates and oxygen. So the fuel, all our fossil fuels come from photosynthesis, and the oxygen we breathe is all coming from photosynthesis. But in our solar cell, we produce electric power. So we take, this is actually one of our dye-sensitized cells. This artificial tree was made by a Japanese research laboratory. It's called Toyota, the car company Toyota, having a big research laboratory. And Toyota Research developed this tree which is using dye-sensitized cells. So we have a green dye that actually, I'll show you later, the structure looks like chlorophyll, very similar chemical structure. But instead of doing the chemical conversion of the electric charges that are produced by light excitation of this sensitizer, we are collecting the current. So the veins you see on these leaves are actually the current collectors. So that's how we pick up the current. And what does the electric power do? Well, not much. It's just make those butterflies flap the wings. Once so it's not a real megawatt power station, but it shows the photoelectric effect very clearly. And actually, the Japanese just laugh. This kind of toys and gimmicks. It's also beautiful. And you can make leaves of fall colors, and because, as I will show you later, the solar cell is different from silicon solar cell. In a silicon solar cell, or any so-called p-n junction solar cell, actually the semiconductor absorbs light and not a dye molecule. And semiconductor generates charges, yes, but it also has to conduct those charges away to the collectors. We don't do that in our system. We have a dye that generates charges, and then other materials are used to conduct those charges away. So there's a separation. It's the only solar cell that separates the light absorption from carrier transport. Carrier means charge carrier transport, negative and positive charges. So I spent a long time on this first slide, and move on and just talk to you a little bit about the problem we're facing. We have the energy demand is growing, no doubt. And so by year 2050, we will need about twice as much energy as today. And just to put this in perspective, today's consumption is about 400 exajoules per year. 1 exajoule is 10 to the power of 18. So 10 to the 400 means 4 times 10 to the power of 20 joules per year. That's what we are consuming today. It's going up all the time, mainly because of growth of the world population and the countries aspiring to higher standard of living and the underdeveloped countries. And so global warming is one of the effects of enhanced fossil consumption. And so we can't do that. We have to stop. There's an emergency that is developing planetary emergency, too much CO2, global warming. And all the oil peak, to top it all up, we have not enough oil to sustain the growth. We have a growth, but the oil peaks. And we have the global warming, and we have the pollution. So it's almost an intractable problem. I mean, to address that, we need to use renewable energy. And so just think about what Thomas Edison said in 1931. He would put his money on the sun and solar energy. I mean, at that time, nobody was thinking about solar energy. This visionary person who invented the light bulb, he thought that there was this law of power. I hope that we don't have to wait until oil and coal run out before we tackle this problem. It seems like we are waiting too long. There is now a real emergency, and we're facing a gap that's as big as our present-day consumption. By year 2050, there will be 400 terawatts needed somewhere. We have to pick it up from somewhere. And so the younger generation, I'm very grateful to the students that came in. The younger generation is particularly challenged to meet those problems and tackle them. And so today I will show you some of the concepts we have developed to collect solar radiation and produce electric power from it. So the prediction on this is, you see the 400 exajoules and going up, but by year 2050 it's almost double the energy consumption. And so we have to cover this by renewable. I mean, it's not all renewables, but there's a huge role to be played. Wind energy, I mean, all renewables have to be used. And so that effort is necessary. And today we are focusing on an area that is between the natural photosynthetic system and the physical PN junction cell. So we started doing scientific studies many years ago. It was actually in year 2000, in 1985. And that experiment, we performed an experiment with tiny little particles of titanium. This is the white pigment that's used on the paint on the wall. It's white, doesn't have any color, doesn't absorb any light, but it is a semiconductor. So it has energy bands that have conduction and valence band. And so these can be used to conduct charges, these energy bands. So we had been injecting electrons by a dye into these tiny little particles. We were the first to make this. Today they're called nanoparticles. We call them colloidal particles. We made those particles in solution, put the dye on, and excite the dye. And we found that could inject charges in those particles very, very rapidly. I mean, it's like nanoseconds, 10 minus 9 seconds, less than a nanosecond. But the charge would remain separated. That was the important observation. And we are stating it in this paper. And so we state also that we had achieved strikingly high efficiency in the sensitization of those colloidal particles. And so the idea was to make this into a cell. And our first cell, they look like that, very primitive. I mean, just a titanium sheet that had those rough structures and the oxide on some surface. And you see the platinum gauze, that was actually the back contact, the counter-electric. You always need two contacts, one for the positive charge and one for the negative charge. And so we had been asked by a local department store, the manager called me up one day and he said, "Professor, are you doing anything useful?" And I said, "What do you mean?" I said, "Well, something that I could show our clients and say, this is something the world could use one day." And so we just have been working on this cell, and I said, "Well, it's still very primitive, but," and he told me, "If it's the world premiere, then I will show it to our clients." And it was. And so we still have good relations to the furniture store today. And so, but then the next generation was already much more sophisticated. This is a thin film of these nanocrystalline particles, very tiny particles. You don't see those particles with your eye. That's why actually you can look through the cell. This is the only solar cell that is translucent. And so it comes in different colors. The choice of the dye gives you that option. And it collects light from all angles. So it's what people call a bifacial cell. It captures light from all angles. And that was a significant distinction to other solar cells because none of them is transparent. None of them uses the concept that the green plant has or employs since 2 billion years to convert solar light to chemical energy. And none of them had this peculiarity to separate the electric charge generation from the transport step. And there's another revolutionary step. Until this publication that came in Nature in 1901, nobody had used rough junctions. This is a three-dimensional film. You can see it's tiny little particles. But this is our junction. So in the physics field, you take a silicon photovoltaic cell, you have positively doped one and negatively doped part, and you make a flat junction. In those days, there was a conviction that you had to use flat junctions, so a flat interface between the positive and negative mobile carriers, silicon. Why? Well, people thought that if you had a lot of imperfections, then it would reduce the lifetime of those carriers, and so you couldn't collect them anymore. So at that time, the paradigm was you had to use perfect crystals and make a flat junction. And here we're coming with this totally disordered, messy-looking film, and you say, well, this is now our photovoltaic device. It was the first of a generation. It's now called bulk junction. Bulk because it has a three-dimensional structure. And the roughness is very high. In other words, if you take this film, you don't see that when you look at the cell, but if I look at the real surface area of this film, it's about 1,000 times higher than the projected geometric area you're looking at. So if you think about a device as a square meter, well, in reality, this is a developed surface that has this roughness to the nanostructure, and it would be like 1,000 square meter real surface. And that you need that to capture the light. That's not there for fun, but it's because we need it to capture the light. And so the scale-up, this is a friend of mine. I just saw him. We had a big conference in Colorado this week. Jonathan Goldstein is the founder of 3G Solar, the company in Israel that develops dye-sensitized modules. And so people like him, they're the entrepreneurs we need to take the invention forward. It's not enough to make a laboratory invention. You have to have people that believe in the invention. Of course, you believe, I believe in it, but I'm not an engineer that designs production steps or production equipment. And also to do that, you need a lot of money. You need to have investors that are ready to risk, that bet on your technology, ready to invest in technology. And so as a poor scientist, you're not ready to do that. So you don't have enough money, unless you happen to be rich. Even then, money will run out very quickly. And so today we have this mass production started in Wales of these flexible cells, and we're going to be building integrated applications. As I mentioned to you, this solar cell is the only solar cell that comes as a translucent glass. And so the idea is to use this principle to make facades. A couple of weeks ago, I was in Tokyo, and we discussed the application of photovoltaic devices in Tokyo. Well, if you put these panels on the roof, you can forget it. I mean, that's not going to produce any significant amount of power. You have to use the facades of the building. And so this technology is particularly suited for building integration, as you can see here. This building is in the Olympic Village in Sydney, and Grätzel is the Australian-based company that commercialized our solar cells. And so you see the integration of the glass panels in the building. So let's step back just one moment and look at the components. We have then the dye that generates the charges. We have those nanostructured particles. The dye is adsorbed onto the surface of those particles. How? Well, that's very easy. You just make the film by screen printing, for example. You put the particles on a glass, and then you just dip the film in the dye solution, and magic step happens. The dye goes on, makes a monolayer, coats the whole film with one molecular layer. Why does the dye do that? Well, it has those anchoring groups. This is chemically designed to do that. We have those carboxylate groups that interact with the surface of the particles. The surface is constituted by titanium ions, and so they get coordinatively attached, and that makes this process a self-limiting. Once the monolayer is formed, then that's it, finished. And so this is very, very nice, because if you had to find a way to spread a monolayer on this very rough surface, well, that would be the end of the story. Never apply that in practical. It has to be simple and quick, and we are facing strong competition, and anything complicated, long, or expensive is a killer. So this is happening on its own. In a few minutes, the dye goes on, the film is colored. And then we have, this is, for example, this is how the cell looks, a look-through cell. These two gentlemen actually made the cell in New Zealand. I saw it one day in Otago News. I mean, I saw it on the internet. Somebody told me. I wouldn't have looked up the Otago News on the internet. And somebody told me, he said, hey, this is David Coyne from the Weizmann and Jim McQuillan. They are in the newspaper. And they had built a cell. And you can see it's perfectly translucent. Also see the fan. I don't know whether you see it, but you see the fan turning. It's very important. The fan turns on diffuse light, because these cells are particularly efficient in diffuse light. I could have brought a cell along and show you the effect here, but I don't dare anymore. I don't dare travel. I used to travel with a kid with the security measures. But I risked to be one hour every time held back at the airport, and I don't want to do that. But I brought a cell along. I'll show it to you later, a flexible cell. So this is the film. These are the nanocrystals again. You see 200 nanometers, small particles. And so the film is spread on the glass. Now, the glass doesn't conduct electricity, so you have to put something that's called a transparent conductor. It's just an oxide that you don't see it, but it does conduct electric power. So that's known technology. So we've used a glass of this type. Use a glass of this type on the back. And then you just have to bring those particles between the two glasses and close the cell, put dye on, and that's it. I mean, it's pretty easy to make. And at the end of my talk, I'll show you how school kids make their own cells. We have actually a competition in our laboratory. Invite from the high school. We invite kids and we show them how to make cells, and it's become much in demand. I have to go to Finland in the next couple of weeks. There's some schools there want to do it, and they wanted me to be there. So it's been so it's a relatively simple process. It's clean. It doesn't use toxic materials. And titanium dioxide, this material is used in toothpaste. It's used as a paint on walls. So it's an anodyne, harmless material. And so, the process we have been developing is very similar to what happens in the green leaf. So in the green leaf, you have these little machines. And you look at it, you don't see it because they're too small. The little machines, that's the chlorophyll generating electric charge. The electric charge is being turned into fuel. That's the carbohydrate that is produced under solar illumination. And so, so we have been mimicking the primary step in the photosynthetic process. Now, I have one scientific slide. I just want to show you from on an energy scale. It's an energy scale. There's high energy, low energy. So the dye has this is the dye potential. This is the energy of the dye. When you excite it, it gains energy. So the light excites. It's like when you get excited, you're more energetic. Okay, people get excited. So it's called the excited state of the dye. It has the photon that's absorbed pumps the electron to a higher energy level. Then you use that electron that electron is injected in these small particles, the conduction band of the small particles. So these small particles just accept charges, the negative charges from the dye, excite the dye, and then we have to regenerate. We leave a hole on the dye. There's a positive charge left because that negative charge has been transferred to the titanium particles. So we need to have now we need to close the cycle. Otherwise, this thing stops right away. You make the charges like capacitive charging. It doesn't make a current electron. So electrons go out, they're coming back in. So we need the shuttle that moves the electrons back to the dye. And so we use a redox shuttle to move the charges back. An electrolyte is usually an ionic liquid. So let me tell you where we stand today. And then I show you some examples. So we have today the conversion efficiency reaches 12%. Sony just announced a module efficiency scale up at 10%, a little bit higher. Tandem 16. Very short energy payback time, good stability. And the industrial development has started, and for a long time I was always asked the question after my talk, well, Professor, if everything is so interesting, attractive, why don't you have any sales of your cells? And so this has now happened. Last year the commercial sales have started. And I'll show you some products later. So there's a lot of things ongoing, like making those beads instead of using small particles. Imagine now if you have those beads. They're also composed of those small nanoparticles of titanium. And so to make the beads, you can put the dye on the bead. Now, just imagine that bead is porous. It has 60% porosity. 60% of this bead is actually air. It's empty. It's a porous volume. And so dye can go in there and you charge the bead with a dye. And when you excite, you bring light in, and the light photon hits those beads. Well, there comes out a surge of electric power. It could take many thousand dye molecules in one bead. And so really, these beads these balls are like little electric generators. And in addition, you get some light bouncing back and forth that contains the light in this structure. So we were able to, we have published recently, it's very simple, this over 10% right away conversion efficiency with those beads. Making also new sensitized. I mentioned to you we have the red, we have a black dye, it's just a structural change. Trying to capture more in the near infrared, because what you want to have a cell that captures all the light below 900 nanometers and converts all these photons in electric current. Now, we are up here with this black curve, we have the so-called black dye, it's this structure. It's 80% conversion. That's not bad at all, because we have some reflection losses. That is an incredibly high number. So 80% of the incoming light photons are converted to electric current. And the Japanese, we can also do it with the green dyes. We can make the green leaf, you saw that. And note that we have here a porphyrin structure that is very similar to the chlorophyll in the green plant. And we published that recently and get a lot of publicity, get 11%. But then the Japanese colleagues, they come up with a marvelous dye. They still don't tell us. They call it dye-X. So just was at the conference, they still don't want to tell us. They're still working on it, intellectual property questions. So, but it's like silicon. It picks up the photons below 1,000 nanometer and see over 80% conversion in electric current, and that's over the whole visible and near infrared. So this shows very clearly the concept is viable, very, very viable, and competitive. We're also using now these ionic liquids. These are melts to avoid problems with solvents, evaporation. We use ionic liquids. These are salts that are liquid at room temperature. Like you take sodium chloride or normal salt, well, that's a solid, but there are salts that are liquid down to minus 80 degrees. And that's the materials we're using. So we have published on those. They have become the favorite materials as electrolyte materials. Eventually, we need to shuttle those charges from the dye to the back contact, and we're using those electrolytes. And so Fujikura just reported these very stable performance. Just think about it, 85 degrees, 85% humidity, over 1,000 hours. If you want to use a module in a house in this facade application, you have to pass these 3 tests. What does pass mean? It means after you have done these 3 tests on the same module, you should have less than 5% degradation. So that's tough. But it's doable with the dye-sensitized solar cell. See here we have the real killer test is 85 degrees, this high humidity. Very strong stress on the cell. One sun irradiation, that's not really a strong stress. The cells are very stable. 8% module level, and this is the minus 40 plus. This is heat cooling. We go from minus 40 centigrade to plus 90. So these cells are stable, and we see now the first of commercial applications. We had this meeting in Colorado. I just come from there. You see production going up. All these have some attractive features. One, I mentioned most of those. We have, for example, we have the multicolor option, transparency, flexibility, lightweight, and so on. And here are some pictures. This is from TDK in Japan, and they see these beautiful multicolored modules. This is from Toyota Aisin-Seki, and they are now, you take it further. The artist comes in and makes these motifs. And one of my Chinese colleagues, she had a Banda beer here that produces electric power. She just, actually, she made the first Chinese cell with the Chinese characters that being. So you can print any motif and will be photovoltaic. That's also a big advantage. Be it the Chinese character, be a panda bear here. So this black part is photovoltaically active. It's about 30% of total area, enough to spin the fan here. And so there are all sorts of architects now interested in this technology because it has this additional features. And so we see a lot of architectural applications. We see, of course, also consumer, the retail. And not least for car, I think the electric vehicles will come, and we need electric vehicle chargers. And I have a flexible cell here that produced commercially already on the megawatt scale, and you just need a little bit bigger piece of that. You could use it to charge your car battery while it's parking in a parking lot. So you feel free to look at this after my lecture. Here's some street lights in Tokyo. This is already a commercial product. You can lease it from Aisin-Seki in Japan. And so these lamps collect light during the day, and then they store it in a battery, and at night the light is coming back through a light-emitting diode. So you don't need electric power for these particular applications. They are all self-sufficient. As I had showed you. Some roof applications. These are some of the first buildings we have been working on with the Aisin-Seki. So what kind of building is that? Well, very useful. And if you go into Nagoya in the city park, you'll find those buildings around. So I mentioned the building integrated, scaled up to bigger buildings. This is a Danish architect, Budke. This is a design, but this is real. This is a photography of the Olympic Village buildings I showed you. You can imagine that you have those walls and multicolored, transparent, the skylights, all producing electric power. And one of the unique selling propositions for the Dyson cell is that we can capture more light during the day because we just collect from a much wider angle with that cell. And so at equal power rating, compared to silicon, the integrated energy, at the end you ask for energy. You don't want power, you want energy, kilowatt hours back from your converter. And so this makes a big difference. It's a big advantage. Also, the silicon panels, they have a temperature problem. When the temperature goes up, the efficiency drops. Well, the dye-sensitized cell, they don't have that. They actually go up slightly in efficiency. So although the formal rating of the dye-sensitized cell is low, if you look in terms of formal rating, you would say, well, silicon is more efficient. But when you integrate over the whole year, you find all of a sudden, well, the cost per kilowatt hour is lower for the Dyson, even though we are rated in efficiency a factor of 2 below. That's because you have these additional advantages from the angular dependency, temperature dependence. And see some other applications. This is the plant here in Cardiff. It's now actually run by a windmill. This is a renewable concept. So they run the plant on a windmill. You saw the pictures. You see the flexible bags. And I don't know whether you know this is this gentleman is Christian Wolfti. He's a new German president. And Doris Leuthard is actually the person who handled the Balzan Prize last year. He's this year's president of Switzerland. And so the two presidents were visiting us on September 9 this year, and we had those computer keyboards. I don't know whether you know, this motif is a Swiss flag. It's a white cross on the red. And this motif is the German flag. And so we really were delighted to see that. And we also gave them a backpack with this flexible cells to charge a light and the battery and phone and so on. German president a little bit skeptical, so his wife is much more optimistic, I would say. So of course, Doris Leuthard had no problem. She put it on her back and walked away with it. So we also had those lamps that Sony provided. These lamps are developed by, they are called Hana Akari lamps. Hana Akari is a Japanese word. It's translated to flower lamp. See, these panels are all photovoltaically active cells. They capture the light, as I said, from all angles. And on this visit, we also showed this lamp that collects ambient light in the room and stores it, and then at night you get the light back from a LED. And I like to introduce this gentleman on the right side, our president, Patrick Eppisch. Can go to mention car charging, very important. In Japan, a race car has been built for 6 million yen. That's a very small budget for building a race car like that. It came in number 7 in a racing against the gallium arsenide technology, but well, it doesn't look really like a car, but it's a very good beginning. And these are flexible, lightweight solar cells. We also saw in Geneva at this spring's exhibition, Hyundai they had equipped their modules with some dye-sensitized. So let me finish. I think my time is up by very much emphasizing the importance of bringing the young people in. And so I'm so delighted to see the students from high school here. This part of the lecture is particularly addressed to the students. Well, I'm a guest professor in Tsinghua University in Beijing, and I was delighted to see how this young girl had been able to build her own cell. I was stunned, and they were of course very good. Tsinghua University is number 1 in China. Extremely good students, and so we have actually in Lausanne showing the high school students. I mean, this was not a high school student. She is a doctoral student at Tsinghua. We can we show the high school students how to make their own solar cells. We tend to use blackberries, but in the winter season it's better to use red cabbage. That's very stable. And it's more efficient if you want to know a secret. Also, hibiscus tea is a very good source. You just have to show it to the presidents when they were visiting. Hibiscus tea, we put the film in, we colored it, made a solar cell, and the fan ran. So that's what we're doing. We're measuring the dye gets extracted, and it goes spontaneously on the surface by self-assembly. I mentioned that to you. Colors the film. If you close the cell, you have something that works. And even go to the younger generation now. We have this was done in the Cité des Métiers in Geneva, and we had even younger kids. And just wanted to show you the infatuation. The infatuation is very important. To have people become passionate about this problem and contribute. And so if I can convey some of that passion and infatuation to students here, then I think it would be a great success of my lecture tonight. So we have already seen some of these features. I like to show at the end of my lecture, the EPFL, the École Polytechnique Fédérale de Lausanne, Lake Geneva, and mountains. We have a very beautiful site. Unfortunately, I don't have a lot of opportunities to look out of the window during the day. So, but it's a beautiful setting. And I like to acknowledge the members of my group. And finally, also our funding, and last but not least, the Balzan Prize International Foundation for having made this great honor to me. And so I feel I feel I was very lucky, and I would like to thank the Prize Committee one more time for having selected me as the Balzan Prize winner 2009. Thank you for your attention.
Thank you so much, Dr. Grätzel. I know that many of you will have some questions to ask, so we'll have a little time. So please go to the microphone and ask your question, and Dr. Grätzel will be glad to answer. Thank you so much again.
What would be the output of that little panel you lifted up and showed us?
2 watts.
2 watts.
Yeah, 2 watts in full-time time.
Okay. Is there a latitude dependence on these?
Well, latitude, yes, but much less than, you mean the AM number, the
Yes,
AMAS
yes.
number. Well, for ourselves, when you take those board sensitizers, there will be a very small effect. But if you take some other solid state devices, of course the AM number can be devastating if you go to higher. If the sun is on the horizon, in other words, you see it as a red ball, how much power is still produced. So the technology we have, is, as I said, is very insensitive to angle and also to spectral distribution. Of course, there is a redshift when you go to the incidence, the angle becomes smaller, the solar spectrum redshift. But we have seen those dyes, they cover up to 900 nanometers, so we are not really losing out there.
Hi, that was a marvelous presentation. The comprehensiveness of it is quite impressive. I'd like to understand, in other words, if we're going in 40 years, if we've got to increase that amount of energy, could you kind of give us some handle on how this type of energy production can replace other types? Or in other words, how can it come in decade by decade? Could you compare, for example, how a Hoover Dam, that level of production of energy and the people it serves, what's the capability of your...
Yeah, that's a good point. Well, I had those in one of the slides. It kind of made an analysis of the different contributions. If you take hydroelectric, how much can we get back from hydroelectric? And I know the figures in terawatt, but it's easy to convert. So in other words, the gap we have, 400 exajoules per year. That's the gap in joules per year, but that's also, you can translate in terawatts, just a different unit. It's a power, it's energy per time. And so, so if I translate that in power, it's 14 terawatts. So you have a gap of 14 terawatts to cover. So how much could be covered by hydroelectric? Not 14, unfortunately, much less, maybe 2 or 3 terawatts. That's what all the hydroelectric potential is. And wind may be very similar. So at the end, the solar potential is evaluated as being easily 50 terawatts. It's actually much more. We get 100, if you look how much, we get 120,000 terawatts from the sun. So we just have to exploit a small part to get those 50 back. If you calculate what the sun gives us as on the whole surface, including the ocean and so on, of course that's not all exploitable, but that gives you the limit. That would be 120,000. And then people say, well, easily accessible is 50. And
so the percentage on the grid, you could replace a grid of electrical generation by 50% with this process?
Well, the grid, I'm a little bit worried about, already now in Germany we see there's some problems with the feed-in of electric power from wind and solar, because it may come at a time you don't need it. And so I think we have to we have to use the power in the house. And the German government just decided to pay more feed-in tariffs if you use that solar power in your own house. And I think that's very wise, because what you want to do with that power is you want to run your computers on it, you want to run your electric car vehicle on it, and
But you could still make the comparison of what you're going to relieve on the other grid. You see what I mean? In other words,
yes,
you don't need as much
yes,
from the...
Yes, of course. That's the same, it's a similar equation, yes. Whatever you produce yourself, you don't have to take it from the grid. You have to less coal power stations needed to get to that power. So that's the name of the game, get less power stations. I was in China in the beginning of September, and we had a long discussion at the Economic Forum. It's the same like Davos. How can China cover in the next 10 years the energy needs? They built a 1 gigawatt power station, coal-fired power station, every other week. And where does the coal come from? Why is the Australian dollar so strong? All from Australia. So this is highly polluting. So this has, you're right, when we start to use less of that power, we save fossil energy. Next question.
Good evening. Thank you for your presentation.
Thank you.
Well, it looks like these dye solar cells have a revolutionary technology. So I have two questions in regards to that. First is, what do you think are the most important obstacles to the widespread commercialization of that? And also, which countries would you identify as the ones leading in the commercialization of these cells? Thank you.
Yeah, we have this
time for one more question.
I wonder if you'd comment on solar concentrators. There's a big facility just beginning in the Mojave Desert that's going online very soon. Could you compare that with with the solar cells, particularly your devices, insofar as efficiency and impact on the environment and cost?
Thank you so much also for answering all these questions. I would like to conclude by telling one thing that I feel very strongly about. All the time I learned when I was a student that good science is beautiful science. And I think that what we saw today was beautiful science. It was beautiful because it went with beautiful technology, with beautiful design objects. And I think this is, I find really very fascinating. And I think that the students here, and I myself, I'm humbled by your presentation because it is, you give us a glimpse of a future that can be even more beautiful than the present that we live now. Thank you very much for your fantastic presentation.
Thank you. That was very nice.
Very nice.